Welcome to another tutorial of a deep learning course. Today we will be talking about self-supervised contrastive learning and look specifically at the method SimCLR, which has been very popular lately. Self-supervised learning is also sometimes called or referred to as unsupervised learning. Basically tries to come up with good ways of how can we learn from unlabeled data. So as we know that all these networks, for instance, also are trained on ImageNet. ImageNet is a huge image library, however, was also very expensive to create in the sense of that you need labels for every image. However, there is, for instance, on the web just so much image data without any labels. And can we actually use these unlabeled data also to pre-train our models to benefit in, for instance, very quickly fine-tune a model to a labeled dataset? Because many image recognition tasks kind of share the same ground, namely understanding images, and then which classes to detect is usually something that, for instance, humans need very little data. This is why when, this idea of self-supervised learning tries to go beyond from pre-trained models on datasets like ImageNet to actually big data, to unlabeled datasets that can be even billions of images, because it's very easy to scale. Just get more images. You don't have to spend anything on labeling. You can even go out yourself and take the images, and with those you can train then your model. In the last 2 years there have been a lot of approaches coming out newly, and one of them, the contrastive learning, is very popular and also easy to implement. So contrastive learning basically tries two things, namely that if we take an image, so for instance this image of a dog, we perform augmentation on it, so standard data augmentation that we have seen before, whether it's grayscale, resizing, color distortion, and so on. And we create basically two views with different augmentations of this image. We push it through a CNN and try to get that the output representations of these two images are similar to each other. This is here this green arrow of saying attract, because we want these two feature vectors to attract, meaning that they are similar to each other. We can do it with a lot of other images as well. However, the feature vectors between images, so basically this image of a dog and share, should be distinct. So they should be different, because these are two different images and we want these representations to represent the actual content of the image. Therefore, we try to push them away from each other and therefore create a feature space in which images that have the same content are close to each other, while images that have different content are therefore far apart of each other. This you also see the augmentation we perform here has then one assumption, namely that what we do in this augmentation we don't care about in these representations. So for instance, if we change the color, we say that the feature vectors here, despite their color differences, should be similar. Therefore, you can already see that picking the augmentations can have a big influence in what your representation look like later. However, we will also see how you can reintroduce these features if they are important for instance, a fine-tuning task like classification. We will then start in this notebook to implement one common method of contrastive learning, see how it works, how we can actually leverage big unlabeled data to train an efficient model that can fine-tune on very little data, and therefore kind of see how we can pre-train on unlabeled data. Let's first start with, again, just importing our standard libraries. There's nothing different. Just as a warning, this notebook is heavy in disk space and also in CPU computation, because we will use a big data set. So therefore just be aware of it, especially if you do it on your local machine. When we have imported our libraries, we can also again download our pre-trained models. So also these models are a bit larger than usual because we deal with larger images now. So therefore just this might take a second or two. Now let's start with discussing SimCLR as an example method of contrastive learning. Before we really dive into the method of SimCLR, let's first look at what data augmentations we want to use, especially for contrastive learning. So we have seen before up here in the figure that what we want to create is we have an image and create two augmentation views of it with different augmentations basically applied on the two. So what we basically here implement is for torch vision, we implement a transformation that takes an image X and returns n views on it, namely that we apply a set of transformation on this image, but with a different seed. What augmentations that could include, as an example down here. So one very popular one is crop and resize that we have also seen before. We take an image, we resize it and crop it back to the original size. We can flip it horizontally. We can do grayscale. We can also change the colors more sophisticated. We can introduce noise, blurring. We can cut out things and so on. So there are a lot of augmentations that we can play around with. And one that has been very important, or especially two, that are in combination important, are crop and resize and color distortion. So crop and resize, you can already see what we have here with the whole view of this stalk gets cropped into a smaller one, for instance here only the tail. And if we now get a second view, which has for instance the head, then the network has to reason that it actually just sees a part of the object, and it probably, this image represents a larger object. Because in order to get these two augmentations up here to be similar in their representation, we need to understand that these two images belong to the same dog and therefore should also have the same representation. This helps a lot in pre-training because this really sees that the network needs to reason about what is in the object, what is in the image, and what objects are therefore there, especially those that are basically centered. The second part is the color distortion, because the problem is if we would just use crop and resize, there's a loophole in it, namely that the network can just check if two images have the same color distribution. So for instance, if I take this dog and have a head and a tail, then we see in both of them we have this huge peak of green in the background, the color of the dog is the same, etc. Meaning that with contrastive learning, so basically just to get the two feature vectors similar, we would just look at what is the average color or what are the main colors in this image, and we would likely already find our pairing image without much of a hassle, without really reasoning about the image. Therefore, this color distortion helps to take away this color, meaning that the network really has to recognize shapes, objects in the image, and through this reason whether two images are the same or not. The augmentations we use here are the ones that also have been proposed already in previous research. So we use horizontal flip, we use the resize and crop, we use color jitter, which basically changes the brightness, contrast, saturation, and also the hue of the image. And one difference compared to the standard contrastive learning parts are here that we use a slightly lower color jitter than before, so we use a lower brightness change, contrast, and saturation. This is because on our dataset here, we have seen that if you do too much color distortion, then you actually get worse performance. So you already see that really changing these small parameters in your data augmentations can have a huge effect on your performance now. We also perform grayscaling, the Gaussian blur that we have seen before, and well, the normalization is basically something we always apply. So these are the transformations that we apply, the data augmentations, and we apply that to a data set which is called SDL10. SDL10 is one that is larger than, so the resolution of the images is larger than cipher 10. So the images are 96 times 96 instead of 32 times 32 pixels. But it has the same 10 classes, or at least it has, again, 10 classes. But we have also a very different data distribution. Namely, we have only 5,000 images labeled per class. However, to basically help us, we also have a dataset of 100,000 unlabeled images that are created the same way as SDL10, where the labeled data is created, However, this unlabeled data has also then a wider variety of classes, so we don't overfit already on 10 classes if we use these unlabeled images. So the question is now, can we use this unlabeled data to pre-train our model to then perform very efficient fine-tuning on these 500 labeled images per class. So let's first get this data set. So this is from Torch Vision. Again, this is quite expensive to download in terms of disk space. So therefore that might also take a while here on Google Colab just to download and unzip. Once this has been loaded, we can now actually look at what happens if we plot images and corresponding transformations of them. So what I do here is I take always an image and just apply 2 times our set of transformations on it. What we get out here is basically you see this deer or this animal has been flipped horizontally. So these 2 images we would want to train to be similar. But you also have, for instance, this boat, which really shows you, on the one hand, we have this global view. So we have one image that shows the whole image and one that just shows a small part of the boat. And to learn that these 2 belong to the same image, we really need to recognize that this one is a boat, basically a sailing boat, that has been then similar in its pattern to this boat. So you already see it is quite challenging to do this task, and this requires reasoning, which we can then take and transfer to classification tasks. Now that we have discussed our data augmentations and we are set with our data augmentations, what is SimCLR, or how can we use these data augmentations in contrastive learning? So SimCLR is called Simple Contrastive Learning Framework, and it has also a simple idea that we have seen before. Namely, we take an image which is X, we apply 2 times the transformations on this image with different seeds, so we get different images out. We apply a network F, which is our representation network, so for instance a CNN, which gets out a representation, and then we apply a small MLP head, which is here represented with G, which tries to project this representation into a space where we want to maximize the similarity between vectors of the same image. So we would want to maximize the similarity between Zi and Zj, and we want to make it as distinct to all other images in our batch. So basically, if we have a batch of 512 images, we would want to make it then different to all other 512 images, 510 images in our batch. There's also a lot of research on, for instance, how this G should be. We use here just a 2-layer MLP, and with a slightly larger hidden layer than in the original paper of SimCLR that has shown on very large datasets to help a lot for us. In this dataset, it helps if you just increase it by a little bit, so basically by a factor of 2 or 4. But you can also try even more around. So this network that you use here is not totally fine-tuned in terms of hyperparameters, and there are still a lot of things you can try out as well. After finishing training a network with the SimCLR, what we do, we throw away this G and use the representation in H. Why we do that and why we not use that is exactly the reason why we, for instance, have color distortion, although the color might be important for our classification. For instance, if we have the classification between a boat and an animal, like for instance a dog, the color can be already a big factor in our classification, namely that boats are simply on water and dogs are usually somewhere inside or on the ground. Therefore, not having this information of what colors are in our image could be quite a disadvantage. And it has been shown that this G basically takes the features of a representation and tries to get out, for instance, the augmentations, meaning that this G often removes then color information, while H can still contain it. And this has been shown that if you take away this G, it works really much better if you run when you're fine-tuning just on this representation. We can see that we actually can fine-tune this F if we have enough data, or we can also just freeze this network F and just create a new MLP that takes from these frozen vectors of H directly a classification to a task, and that can already work quite well. So we have talked already a bit about what loss function can be, meaning that we want to increase the similarity between two vectors of the same image, just different augmentations, while trying to minimize the similarity for all others. And one loss that is very much basically that in mathematic formulation is the info as an NCE loss, which nothing else is written down here, and if you look closely, it is actually a softmax over similarities. So for a given vector zi, so for one image, we try to classify in the sense that zj is the other image, and we classify it over all other representations in our batch. So this is then indeed nothing else than trying to maximize this similarity while trying to minimize the similarities to all other images. You see that we have, for instance, here just a similarity function, meaning that we can use different similarity functions. A very common one here is cosine similarity that we have also seen before, so simply the dot product divided by the length. The tau here is the temperature parameter, because you can imagine if I have 1,000 batch, my batch size is 1,000 or even larger, then just this denominator can increase quite a lot, because the cosine similarity has a minimum of -1 and a maximum of 1. So what this tau then helps is really to also have you a wider range of where you can go with your classification in that sense. Now that we have seen all of this theory and the idea behind SimCLR, let's try to actually implement it into one nice framework. So we use again PyTorch Lightning here, and what we do is we create our ConfNet, which is the base model F that we have seen before. For this we just use the standard ResNet 18. And for the G, as said before, we have an MLP that takes a linear layer, a ReLU, and then basically another linear layer. And in our forward paths, what we do is we apply this info and NCE loss. So as our batch, what we have given is a batch of images where each image is twice in it, but with different augmentations. So the first thing we do is we run our ConfNet on these images to create features. We calculate the cosine similarity between every pair of images, and then we try to find which ones should be similar and which ones should not be similar. So which ones basically are the positive examples for each image and which ones are the negative examples. And this we take to then calculate our info and NCE loss and return the loss. The part down here is basically for logging, so that we can also see if I would now rank all my images, how often is my correct image in the top 1 or top 5, etc. Finally, then we have basically the training step and the validation step to run with. The training, as said before, we can now just go ahead and take our unlabeled dataset and throw it onto SimCLR. So you see also this whole forward pass doesn't use any labels. Basically here we throw away our labels if we have given any. And therefore we can just use our huge unlabeled dataset and apply SimCLR on it and let it run for quite some time. The batch size is often also an important parameter, so you can use even larger batch sizes. Usually if you have a lot of data, it's shown that the larger your batch size, the better the results. But here, because we don't have an infinite large data set, 256 showed to be already sufficient. And the other parameters like the temperature, you also have to adjust for the batch size as well as the weight decay and etc. So now let's execute it and look actually at the tensor board at how does the training curve of such a model look like. So let's look at, for instance, the top 1 accuracy in the training, and you see that after training we achieve about 95% top 1 accuracy, meaning that the most similar image for one image in the batch is actually the correct other image, the other augmentation of it. So therefore you see only 95% is quite good, because that shows that we find the corresponding images here. Also on the validation we can see it actually does almost as well as before, as on the training, so there's not really overfitting happening here. But you can also see based on the time that we say here, it trained for more than a day on a GPU of 24 gigabytes. So contrastive learning can also take quite some time, and the training curve also doesn't suggest that it might have finished already. So if you would let it train even longer, you might get even better results. However, we found that this for now is here sufficient for the model to just showcase it here. Contrastive learning, however, can still be then also expensive in really finding the best models.